Alright, what's up guys? In this video I'm going to pick up some multivariable calculus, and we're going to be back on the topic of triple integrals. We're going to evaluate another iterated integral. So the integral is already set up for us here, and we just need to evaluate it. Okay, so we got this triple integral from 0 to ln of 8, from 1 to the square root of z, and then from ln of y to ln of 2y. And the function is e to the x plus y squared minus z dx dy dz. So it's just a triple integral, and we just kind of gotta work through it. All right, so we know that we're going to be integrating with respect to x first, work our way from the innermost to the outermost integral. So it's going to be from ln of y to ln of 2y. And we have our function e to the x plus y squared minus z integrated with respect to x. That's how we're starting off. Okay, so although we are integrating with respect to x, notice how in terms of our function, this is an exponential. So we got x plus y squared minus z. We can't extract the y or the z from this because it's a part of the function. So what you're going to have to do is do a u substitution and try to fix that here. So we're going to pick u to be what's at the top, which would be x plus y squared minus z. We'll need to take the derivative of that. And if we take the derivative of that with respect to x, we'll get dx. And then what we'll end up having is just the integral of e to the u du. Okay. Now we do need to change the limits, but it's relatively straightforward to change the limits in this particular scenario, because all we have to do is substitute in ln of y and ln of 2y. We know that if we integrate e to the u du, we're going to get e to the u. So I'm just going to plug the limits onto the end here. Well, actually, I need to plug them here as well so that you can see. So if we plug in substitute in our previous limits, we'll get ln of y plus y squared minus z for the lower one. And then for the upper one, it looks like we'll get ln of 2y plus y squared minus z. So we already know what the antiderivative is. So this would be ln of y plus y squared minus z ln of 2y plus y squared minus z. And we substitute in, applying the fundamental theorem of calculus, and it looks like we're going to get 2y e to the y squared minus z if we sub in the upper limit. Subbing in the lower one, we'll get y e to the y squared minus z, which we could effectively just write as ye to the y squared minus z. And that'll get us down to our double integral now. So now we're on to the double integral. So it's from 0 to ln of 8, from 1 to the square root of z. And then we have ye to the y squared minus z, and this time with respect to y. Also, don't expect all the time your limits of integrations to be numbers. They won't always be that sometimes, especially with these double and triple integrals. Don't be surprised if you see something like the square root of x or something crazy like that as the limits. Doesn't always have to be a value. All right, so now that we know that we're integrating with respect to y, we're going to have to use the limits for the innermost integral. And what we're going to need to do in this particular scenario is another substitution. Now, in situations like this, where you have to do more than one substitution, you don't want to use the same variable. I see students doing that a lot. And what ends up happening is, if you use the same substitution variable, you're going to get lost. Again, substitutions, you can choose any variable you want, any letter in the alphabet. If you want to use Greek letters, that's fine, but you need to use something different than what you started with. Otherwise, it's going to be tough to kind of follow. And in this particular scenario, I'm going to use w. I'm going to go a little unconventional. And I'm going to pick w to be y squared. And you'll see the reason why I didn't pick it to be y squared minus z. I'll explain that in just a moment. And so then dy is 2y dy And so we'll end up with 1 over 2y dw is equal to dy. Okay, so we can pull out a 1/2, and then what we'll have is, after we do some simplifying, we'll have e to the negative z plus w integrated with respect to w. Actually, let me write it like this. I'm going to write it as 1/2 times e to the negative z, and then we're going to change the limits, and we'll just have e to the w dw. Now we'll need to change the limits. That won't be hard to do at all. That's just going to be 1. If I square 1, I get 1, and if I square the square root of z, I just get z. So this would be z from 1 to z. And so we got our 1/2 e to the negative z on the outside. This is e to the w evaluated from 1 to z. And so when we multiply by that constant out there, we'll get 1/2 e to the negative z multiplied by e to the z minus e, because e to the first power is e, and obviously we stick in a z for the w. And now we can essentially move to our last integral, but we're going to expand out this expression a little bit to make it a little easier. And so what I'm going to do, the 1/2 is still a constant. Now we aren't integrating with respect to z now, so this would be from 0 to ln of 8, and I'm gonna write it as 1 dz minus the integral from 0 to ln of 8. It's going to be e to the 1 minus z dz. And hopefully you're seeing how it's getting a little messy, and that's the reason why a lot of triple integrals, not all the time, but can be quite nightmarish to deal with when things are in Cartesian coordinates. That's why a change of coordinate system sometimes is beneficial for evaluating triple integrals, because doing it in Cartesian coordinates can just be a nightmare in terms of work, and doing things in spherical coordinates sometimes it's a lot better. So that's the purpose of it. So now that we've broken up the last part here, and again, all I did was, after we took care of essentially the double integral, now we're down to the single one. All I did was, after we plugged everything in, applied the constant multiple rule, I expanded out the inside. I just moved the 1/2 out, it's just a constant, and now we're breaking it up a little bit, just in case you got lost. So let's deal with them individually. So from 0 to ln of 8, 1 dz. Well, that's just 3 ln of 2, because remember that ln of 8 can be written as 3 ln of 2. And if I'm integrating 1 with respect to z, I just get z, and you would plug in the limits. And then the next one is from 0 to ln of 8, and we got e to the 1 minus z integrated with respect to z. Now, I do know what the antiderivative to that is, but I'm gonna show you the steps. So do a substitution. Again, use a different variable. You don't want to use the same one. So I'm just going to go a little unconventional. I'm going to use v, and we're going to set v equal to 1 minus z. That means we need dv, which would be negative dz. Okay, and what's going to happen is we're going to bring our negative to the front of the e, and we're going to get negative e to the v dv. Okay, and what we're going to have to do is change the limits again. Now we substitute in the 0, and then we substitute in the ln of 8. Okay, so we just get 1 minus 3 ln of 2, because again, ln of 8 can be written as 3 ln of 2. But we'll need to flip the limits and change the sign of the integral. So we'll have our negative on the outside, then we'll have our negative in here, so we'll get negative e to the v dv. And again, the limits are from 1 to or excuse me, from 1 minus 3 ln of 2 to all the way up to a positive 1. The negatives make positives, so this is e to the v, and we evaluate it from those limits. And you see what you get. So we're going to get e, looks like we're going to get e over 8. It's better to write as e over 8. Now, if we go back, we pulled the 1/2 out front. Now, when we broke this up, when we got down to the last integral after doing the double, we got down to a point where we split it up. Now, we split the integral up. That made it a little easier. Remember, this was 3 ln of 2. And then for this one, we ended up getting e minus e over 8. So now what we'll need to do is simplify a little bit. And we're almost done. So the 1/2 was pulled out. So we got 3 ln of 2. And it was e minus e over 8. Now on the inside here, let's take care of the negatives. If I distribute in the negative for e minus e over 8, that essentially just end up becoming negative e plus e over 8. And so we would then have to subtract. So we would have 3 ln of 2 minus e plus e over 8. Now we need a common denominator. So what we can do, since we have a common denominator, we'll need a common denominator, excuse me. So since we got 8 here, we obviously want to get a common denominator of 8 for both pieces. So we're going to multiply the numerator. We're going to multiply 3 ln of 2 by 8, this e by 8, and we also have to divide by 8 as well, because we won't have common factors. So this would be, or common denominators, so this would be 3 ln of 2 multiplied by 8 all over 8 minus 8e all over 8, and then this would be plus e all over 8. So we need a common factor of 8. Okay. And we just got to break this down a little bit and see what we get. Okay, so we know that 3 times 8 is 24. So it looks like what we'll get is 24 ln of 2. And this is going to be minus 7e. And we obviously have a common denominator of 8. Okay. Now, if we multiplied all of that by 1/2, we would have to divide by 2 down here. And so essentially what happens at this scenario, we'll get 24 ln of 2 minus 7e. And essentially what happens is the 8 would come down, so we'd have 2 times 8, which is 16. So we would get all over 16. And that would actually be your answer. So your final answer for this integral is a triple integral from 0 to ln of 8 from, I'm sorry, this was from 1, excuse me, from 1 to the square root of z, and then from ln of y to ln of 2y, and we had e to the x plus y squared minus z dx dy dz, and our answer here is a funny looking number, but it is the answer. And unfortunately, that's just life with math. Sometimes the answer will look a little ugly, but it's still the answer even if it looks ugly. So that's going to be the solution here. So that one required a little bit of work. Again, this was a triple integral that I literally went to the example section from the calculus textbook, and I just pulled out, because after I graduated and I got my physics degree, I just kind of kept the calculus textbook. I actually purchased it so that I could practice problems as much as I want. It's helped for grad school, of course, but that's essentially what I did. And so every calculus textbook should have a section with just some practice integrals, and this was one that I saw in there in the example section, and so I said, well, why not try it? So all right, that's your answer. So let me know if you got any questions, and I'll see you next time.